Hello, in this video I will be presenting our paper RbA segmenting unknown regions projected by all to be presented at ICV 2023. In this paper we tackled the problem of unknown segmentation in which we have two goals. The first goal is to segment known classes which are presented during training and also to segment unknown regions that have not been seen during training. Previous state-of-the-art methods are methods that use outlier supervision during training, and we will talk about two. First of all, we have Pebble, which was presented at ECCV 2022, the idea being to optimize energy with abstention learning using outlier data. And also we have dense hybrid, in which they also use outlier data to optimize energy with a hybrid anomaly score that combines generative and discriminative modeling of the data. The limitations of these methods can be summarized as follows. First of all, we have a lack of objectness in which the anomaly score is not uniformly assigned throughout the object, and also high false positives. Like we can see that known regions sometimes get high anomaly scores, and also due to fine-tuning with outliers, there's a negative effect on the main task also, as we show in our experiments. Our motivation is how can we obtain better objectness? Most of these previous methods are built using per pixel classification models, and these can be characterized as the ones consisting of a backbone, decoder, and a classification head in which the supervision is being applied per pixel. The goal of this work is to explore mask classification for unknown segmentation. Unlike per pixel classification, where a label is being predicted for each pixel, in mask classification, the idea is to predict masks and then assign a label for each of those masks. The first methods that propose this paradigm are mask former and mask to former. The difference in terms of architecture is that we have some learnable queries that interact with the image features using a transformer decoder, and the supervision is being applied on the semantic level, and the mask supervision, they are applied separately. So to explore the potential of mask to former for expressing uncertainty, we do the following. We first of all notice that some of the object queries are specialized in predicting certain classes, and we show this using this heat map in which the x-axis represents the query IDs and the y-axis is the classes, and we can see that there's a one-to-one correspondence between some of the queries and the classes in which the queries consistently predict each of those classes with high confidence. Apart from being the specialization, we also see that specialized queries are independent. This means that if we, for example, after identifying each query that focuses on a certain class, by isolating these queries and using them to predict the intersection, to predict or segment a certain class, and compute the intersection of reunion scores, we can notice that the performance still remains pretty competitive. And the masking can be done in two ways, either by isolating them before the transformer decoder using hard masking, or soft masking after the transformer decoder. And when we look at the per class IOU scores, these are the original values without applying any masking. With soft masking, we can see that the performance is still consistent across most of the classes, and even with hard masking, the performance is still competitive. So the specialized queries are independent, so we would like to interpret these queries as one versus all classifiers, and therefore we define the outlier score as the probability of being rejected by all of the queries. The score can be computed as follows. After we take the output logits from the mask to former model, we can apply some normalization to make the probability of a certain class between 0 and 1. And then basically we define the event of being an outlier as belonging to the class K plus 1 as the complementary event to belonging to the known classes. And by assuming the mutual exclusiveness of the events, we can basically turn this union into a sum. And therefore, we can, by dropping this constant, we can obtain our RbA score as follows. We also try to encourage the one versus all behavior by using outlier data. The idea is to take the pixels from the unknown regions and then try to suppress those pixels such that they become lower than a certain threshold using the squared hinge loss as follows. Here's an overview of our method. The advantages is that, first of all, RbA preserves objectness, as you can see here, and also it eliminates uncertainty at boundaries. We show results on the segment if you can benchmark both the anomaly track and the obstacle track for the per pixel metrics and the component level metrics, and we can see that RbA with and without outlier supervision outperforms most existing methods. For fair comparison, we also implement both methods, Pebble and dense hybrid, on mask to former architecture, and we see that they cause a certain drop in MIOU scores compared to the original, and RbA is capable of preserving the IOU and also outperforming the methods in terms of unknown metrics. Here are some results on the anomaly track of segment if you can, in which we compare with Pebble and dense hybrid with both of their mask to former and per pixel architectures as follows. Here's a video of RbA being applied to real-life videos in which you can see that a car that is moving towards the road that is classified as OOD once it leaves the ground.